You think you understand hot and cold. You touch a stove, you pull your hand back. You drink coffee, it warms your belly. You step outside in winter, you shiver. Hot and cold seem obvious. They seem like the most basic sensations in the world. But that's not temperature. That's just your nerve endings firing. That's biology lying to you about physics. Most people walk around thinking temperature is like a ladder, cold at the bottom, hot at the top. Absolute zero is the floor. And the ceiling, well, you figure it just goes up forever. Hotter and hotter without limit, like counting numbers. 1, 2, 3, infinity. Here's the problem with that comfortable picture. It's completely wrong. Temperature doesn't work like a ladder. It works like something much stranger. And when you really understand what temperature actually is, when you dig into the mechanics of hot and cold, you discover something that will genuinely melt your brain. There's such a thing as infinite temperature, and beyond that, there's something even hotter, negative temperature. And negative temperature isn't cold. It's the hottest thing possible. Let me show you what I mean. You drink hot coffee, you wait, it gets cold. Simple, right? You've done this 1,000 times. Every morning, coffee starts hot, room is cool, heat flows from the coffee to the room. Eventually, they're the same temperature. Done. Nothing mysterious. But stop. Stop and actually think about what just happened. Ask yourself the real question. Why does heat flow that way? Why doesn't the cold room make the coffee hotter? Why doesn't heat flow backward? Why doesn't the room steal cold from the coffee and become colder while the coffee heats up? Most people say that's just how it works. Hot goes to cold. That's the law. But that's not an answer. That's just repeating the observation with fancier words. You haven't explained anything. You've just renamed the mystery and moved on. You stand in a hot shower. The water warms you. You step outside on a winter day. The air cools you. Hot food on your plate gets cold. Ice cubes in your drink melt. You experience temperature every single day of your life. You think you understand it. Here's what's really happening, and it's going to destroy everything you think you know about temperature. You think temperature is a measure of how fast atoms are moving. Faster atoms mean hotter stuff. Slower atoms mean colder stuff. Simple scale from cold to hot. Zero at the bottom. Numbers getting bigger and bigger toward infinity at the top. Like a thermometer that goes up forever. Like a ruler that stretches into the sky. Wrong. That picture is so incomplete, it's almost a lie. It's the kind of thing we tell children. It's useful. It's not true. Temperature is not speed. Temperature is not energy. Temperature is not how hard atoms are bouncing around. Temperature is something far stranger. Temperature is about probability. It's about how energy is distributed among particles. It's about disorder. It's about counting. Let me show you what I mean. Take a box of gas. Trillions of atoms bouncing around in there. Some moving fast, some moving slow, some moving in between. They're all colliding with each other, exchanging energy. The speeds are constantly changing. The temperature of that gas is not the average speed of those atoms. That's the lie they told you in school. The temperature tells you the shape of the distribution. How many atoms are slow? How many are fast? How many are in between? What does the curve look like? At low temperature, most atoms are slow. A few are fast. The distribution is bunched up at low energies. Almost all the atoms are moving gently. Only a rare few are zipping around. At high temperature, the distribution spreads out. More atoms have high energies. More atoms are moving fast. The curve flattens. Energy is more evenly spread across the population. Now here's the question that breaks everything. What happens when you keep adding energy? Does temperature just go up forever? Think about it. You heat the gas more and more. Atoms move faster and faster. Temperature climbs higher and higher. 1,000 degrees, 1,000,000 degrees, 1,000,000,000 degrees. Does this ever stop? For a normal gas, no. You can keep heating it. Temperature keeps rising. There's no upper limit. At least not until you hit ridiculous extremes where physics itself breaks down, where space and time stop making sense. But here's where it gets strange. Not all systems are like a gas. Some systems have a ceiling. Some systems have a cap on how much energy they can hold. And that's when temperature stops behaving the way you expect. Imagine something different from a gas. Not a gas with unlimited energy states. Something simpler. Something with a cap. Something with a ceiling. Think of atoms that can only be in two states: ground state or excited state, low energy or high energy, nothing in between, like coins that can only be heads or tails, like light switches that can only be on or off. This isn't fantasy. Real quantum systems work like this: nuclear spins in a magnetic field, certain atomic transitions, quantum bits in a computer, two states, that's it. You have 1 million of these atoms. At low temperature, most are in the ground state, most are low energy, a few are excited. The system is ordered, predictable. If you picked a random atom, you'd bet it's in the ground state and usually be right. You add energy, more atoms flip to the excited state, the temperature goes up, still normal. This matches your intuition. Add heat, temperature rises. You add more energy, more atoms flip. Now it's getting interesting. You add more energy, half the atoms are now excited, half are in the ground state, 50 to 50 split. Even odds. If you pick a random atom, you have no idea which state it's in. Maximum uncertainty. Here's the question: what is the temperature at 50 to 50? Stop and think about it. At low temperature, the system is ordered. Most atoms low energy, predictable. At 50 to 50, the system is maximally disordered. Every atom has equal chance of being high or low. Maximum randomness, maximum chaos, maximum uncertainty. You can't predict anything. The temperature at 50 to 50 is not just high, it's infinite. Infinite temperature. Let that sink in. When half your atoms are excited and half are in the ground state, the temperature is infinite. Not 1 billion degrees, not 1 trillion degrees, not a number so big you can't write it down. Infinite. Actually infinite. Wait, how can temperature be infinite? That sounds like nonsense. That sounds like a math error. That sounds wrong. Here's the thing. Temperature is defined mathematically as the inverse of something called the entropy gradient. I'm going to say that again without the jargon. Temperature measures how much disorder changes when you add energy. At low temperature, adding a little energy increases disorder a lot. The system was very ordered. Now it's less ordered. Big change. Temperature is low. At high temperature, adding a little energy increases disorder only a little. The system was already pretty random. Now it's slightly more random. Small change. Temperature is high. At 50 to 50, adding energy doesn't increase disorder at all. Zero change. Why? Because the system is already at maximum disorder. You can't make it more random. It's already as random as it can possibly be. Half up, half down. Maximum entropy. Maximum chaos. When you add energy to a 50 to 50 system, you're not increasing disorder. You're just shuffling which atoms are up and which are down. The total randomness stays the same. And mathematically, temperature is 1 divided by how much entropy changes when you add energy. When entropy doesn't change, you're dividing by 0. And when you divide by 0, you get infinity. That's not a trick. That's not a mathematical artifact. That's not a glitch. That's the actual definition of temperature, telling you that 50 to 50 is infinitely hot. But here's where your brain should explode. What happens if you add more energy? What if you push past 50 to 50? What if you force the system beyond maximum disorder? You've got 50 to 50, half excited, half ground state. Infinite temperature, maximum disorder, maximum randomness, the entropy peak. Now you force more atoms into the excited state. 60% excited, 70% excited, 80% excited. What happens to disorder? Think about it carefully. It decreases. At 50 to 50, every configuration is equally likely. Maximum randomness. If you shuffled the atoms and looked at the result, you'd have no idea what to expect. Pure chaos. But at 80 to 20, the system is ordered again, just ordered in the opposite direction. Most atoms are high energy instead of low energy. If you picked a random atom, you'd bet it's in the excited state, and usually be right. Predictable, ordered, just inverted. Adding energy past 50 to 50 makes the system more ordered, not less. Entropy goes down. Disorder decreases. The system was at maximum chaos. Now it's becoming organized again, but organized upside down. And here's the kicker. Here's what should make you question everything you thought you knew. When entropy decreases as you add energy, the temperature becomes negative. Negative temperature. Not cold, not below 0 Kelvin, not frozen. something far stranger. A system with negative temperature is hotter than infinite temperature. I know that sounds insane. I know that violates everything you think you understand. How can anything be hotter than infinity? Infinity is supposed to be the end, the maximum, the biggest number. Here's the test. Here's how we know. Here's the proof. Put a negative temperature system next to a positive temperature system. What happens? Heat flows from negative to positive. The negative temperature system gives energy to the positive temperature system. Why? Because heat always flows from hotter to colder. That's not a rule we made up. That's the second law of thermodynamics. That's what happens when the universe shuffles toward maximum probability. So if heat flows from negative T to positive T, the negative T system must be hotter. Hotter than any positive temperature, hotter than infinite temperature, hotter than infinity. Let me lay out the real temperature scale for you. The one nobody told you about. The one they left out of your education. Start at positive 0 Kelvin, coldest possible for normal systems. Absolute zero, all atoms in the ground state. Perfect order, no motion, no randomness, complete predictability. Go up. Positive temperatures increase. 100 Kelvin, 1000 Kelvin, 1,000,000 Kelvin. More and more disorder, more atoms excited, getting hotter, entropy rising. Keep going. Temperature approaches positive infinity. The 50 to 50 split, maximum disorder, infinitely hot, entropy at its peak. Now here's the part that breaks the scale. Cross over. Negative infinity and positive infinity are the same point. They meet at maximum disorder, at the entropy peak, at 50 to 50. Then as you add more energy, you enter negative temperatures. Negative infinity first, then negative temperatures increase toward negative 0. At negative 0, almost all atoms are excited. Perfect order again, but inverted order, high energy order, the mirror image of absolute 0. So the real scale goes from positive 0 Kelvin through all positive temperatures up to positive infinity Kelvin. From there, it wraps around to negative infinity Kelvin, continues through negative temperatures, and finally approaches negative 0 Kelvin. In terms of hotness, the order is positive 0 Kelvin, the coldest, then increasing through positive temperatures up to positive infinity, followed by negative infinity, and ending at negative 0 Kelvin as the hottest state. Negative 0 Kelvin is the hottest thing possible. Not hot in the sense of fast-moving atoms, not hot in the sense of high numbers on a thermometer. Hot in the sense of will dump energy into anything it touches. Hot in the sense of heat will flow out of this system into any other system in the universe. You're thinking this is theoretical nonsense, mathematical games, physicist word tricks, not real physics, not the actual universe. Wrong. We've made negative temperature systems. We've measured them. We've used them. They're real. They're in your house right now. Edward Purcell and Robert Pound, nuclear magnetic resonance experiments at Harvard. They took lithium fluoride crystals, applied magnetic fields to align the nuclear spins, all spins pointing one direction, ordered, low entropy, positive temperature. Then they did something clever. They flipped the magnetic field faster than the spins could respond, faster than the system could relax. The result? More nuclear spins in the high energy state than the low energy state. Population inversion. The system was ordered, but upside down. Entropy was low, but on the wrong side of the peak. Negative temperature. The system was hotter than infinite. It immediately started dumping energy into its surroundings. Heat flowed out. Entropy increased. The system relaxed back to positive temperature. But they measured it. They proved it. Negative temperature is real. And here's the thing. You've seen negative temperature 1,000 times without knowing it. Lasers. A laser works by population inversion. You pump energy into atoms until more are in excited states than ground states. You force the system past 50 to 50. You create negative temperature for those atomic transitions. That's why lasers are different from light bulbs. A light bulb has positive temperature, atoms in thermal equilibrium, random emission, incoherent light going in all directions. A laser has negative temperature for the lacing transition, population inversion, stimulated emission, coherent light, all photons marching in step. Every time you see a laser pointer, a barcode scanner, a laser printer, a DVD player, you're seeing negative temperature in action. You're seeing something hotter than infinity doing useful work. Now you can understand why heat flows the way it does. Heat doesn't flow from hot to cold because of some mysterious rule imposed on the universe. Heat doesn't flow because of a law written in stone. Heat doesn't flow because God said so. Heat flows because systems evolve toward maximum disorder. That's all thermodynamics is. Probability, statistics, counting. A hot system next to a cold system has low total entropy, energy concentrated in one place, few ways to arrange things, improbable configuration. As heat flows, energy spreads out. More atoms share the energy, more ways to arrange things. Entropy increases, disorder increases. The universe shuffles toward the most probable state, the most likely configuration, the one with the most ways to be arranged. For normal systems, this means heat flows from high temperature to low temperature. The high temperature system has excess energy. The low temperature system has a deficit. Sharing increases total disorder. But for negative temperature systems, this means heat flows from the negative temperature system to the positive temperature system, because that increases total entropy. That moves toward maximum disorder. The negative temperature system is hot precisely because giving away energy increases disorder. It's ordered in the wrong direction, inverted, and the universe wants to fix that. The universe wants to shuffle it back toward maximum chaos. Heat flow is just probability winning, every time. Okay, so -0 is theoretically the hottest, but that requires bounded systems, special conditions, two-level systems, quantum constraints. What about normal matter, regular stuff, gases and solids and liquids? For ordinary stuff, unbounded systems, where atoms can have any energy, is there an upper limit? Yes, but it's ridiculous. It's so big it makes no sense. The Planck temperature, about 1.4 times 10 to the 32nd power Kelvin, 1 followed by 32 zeros, 100 million trillion degrees. At this temperature, quantum gravity effects dominate. The wavelength of thermal radiation becomes smaller than the Planck length, smaller than the smallest meaningful distance. Space and time themselves start to break down. Our physics can't handle it. Our equations return nonsense. We don't know what happens. For comparison, the center of the sun is about 15 million Kelvin, hot by human standards, nothing compared to Planck temperature. The Large Hadron Collider creates temperatures around 1 trillion Kelvin when protons smash together. Still nothing. Still a factor of 10 to the 20th away from Planck temperature. The early universe, moments after the Big Bang, fractions of a second after everything began, approached the Planck temperature. That's the hottest the normal universe has ever been. But for bounded quantum systems, you can exceed even this. Negative temperature is hotter than Planck temperature, hotter than the Big Bang, hotter than anything conventional physics can describe. Because negative temperature systems will dump heat into anything, including systems at Planck temperature. The hottest thing is not a big number. The hottest thing is a negative number, approaching 0. Come back to your coffee. That cup sitting on your desk, steaming, cooling, ordinary. What are you actually watching? You're watching trillions of molecules, water molecules, coffee molecules, all bouncing around, all exchanging energy through collisions. Your hot coffee has a certain distribution of molecular speeds. Lots of fast molecules, spread out distribution, high entropy. Your cool room has a different distribution. Fewer fast molecules, bunched up distribution, lower entropy in that sense. When they interact, molecules collide at the boundary. Fast coffee molecules hit slow air molecules. Energy transfers, little packets of energy jumping from coffee to air. The coffee's distribution shifts down. Fewer fast molecules. The room's distribution shifts up. More fast molecules. The distributions approach each other, not because of a rule, not because of a law, because of probability. There are astronomically more ways for the energy to be spread out than concentrated. There are vastly more configurations where coffee and room have similar temperatures than configurations where one is hot and one is cold. The coffee doesn't cool because it has to. The coffee cools because it's overwhelmingly probable. The universe is just shuffling, and shuffling leads to spread, and spread is what we call equilibrium. And the temperature? The temperature is just telling you what that distribution looks like, how probable different energy states are, how disordered the system is, where it sits on the road from order to maximum chaos. Low temperature means ordered, concentrated, energy bunched up, predictable. Infinite temperature means maximum disorder, energy spread evenly, 50 to 50 for everything, completely unpredictable. Negative temperature means inverted order, energy piled in the high states, ordered backwards, ready to dump everything into anything it touches. Your coffee is traveling from order through disorder, from hot through warmer room. If you had the right kind of system, you could push it through infinite and beyond infinite into negative. Here's what this means for your understanding of the universe. Temperature is not a simple scale. It's not a thermometer reading that goes from low to high. It's not a number that just gets bigger and bigger. Temperature is a measure of how energy is distributed, how ordered or disordered a system is, how it will interact with other systems, which way heat will flow. And that means temperature can do things your intuition says are impossible. It can be infinite, it can be negative, it can be hotter than infinite. It can wrap around on itself in ways that make no sense to common experience. This isn't philosophy. This isn't word games. This isn't physicists being clever. This is measured, tested, used, practical. Every laser you've ever seen proves it. Every MRI machine uses nuclear spins in ways that touch these ideas. Every quantum computer manipulates populations in ways that invoke these principles. The universe is stranger than your common sense allows. Your intuition was built to throw rocks and avoid predators on the African savanna. It was not built to understand statistical mechanics. It was not built to handle infinities and negative temperatures and probability distributions over energy states. When you ask, how hot can it get, you're asking the wrong question. You're assuming temperature is a simple number that increases without bound, like counting. 1, 2, 3, 4, up and up forever. The real answer is, temperature is a way of describing probability distributions. And for the right systems, that description requires infinities and negative numbers. The scale wraps around. The hottest thing is not a big number. The hottest thing is a small negative number. Maximum hotness isn't a trillion degrees. Maximum hotness is -0 Kelvin. A perfectly inverted, perfectly ordered system ready to dump all its energy into anything it touches. Ready to heat up the entire universe if you let it. I know this is uncomfortable. I know you wanted a simple answer. You wanted me to say a trillion degrees, or the center of a supernova, or the Big Bang was the hottest, something you could picture, something that fits on a thermometer, something that matches your intuition about hot and cold. But the truth is stranger and more beautiful than that. Temperature is not what you think. Heat is not what you think. Hot and cold are not what you think. These everyday concepts, the ones you've used your whole life, the ones that seem as obvious as breathing, they're approximations, useful approximations, good enough for coffee, good enough for weather, good enough for cooking. But they hide a deeper structure. They hide infinities. They hide negative numbers. They hide probability distributions that wrap around themselves. And when you peel back the layers, when you look at what temperature really means, when you stop accepting the kindergarten version and demand the real thing, you find the universe is more interesting than you imagined. That's not a failure of explanation. That's not physics being difficult on purpose. That's what understanding actually looks like. Not comfort, not familiarity, not simple answers that make you feel good. Truth. Next time you touch something hot, stop for a moment. Think about what you're really feeling. You're not feeling heat as some substance flowing into your skin. You're feeling energy transfer driven by probability. You're feeling the universe shuffle toward maximum disorder. You're feeling the statistical mechanics of trillions of atoms finding their way to the most probable configuration. Your coffee cools because disorder increases. Lasers work because we create inverted order. Negative temperature is real and hotter than infinite. The temperature scale wraps around itself in ways that break intuition. The physics underneath your everyday experience is spectacular, strange, counterintuitive, beautiful if you let it be. And you can understand it, not by trusting your gut, not by relying on common sense, but by learning what temperature actually means, by accepting that the universe doesn't owe you simple answers, by building new intuition based on mathematics and measurement instead of rocks and predators. Now you know what nobody told you. Temperature can be infinite. Temperature can be negative. Negative is hotter than infinite. How hot can it get? Hotter than you ever imagined. all the way past infinity and out the other side.